Hi, let's do this question. We need to find expression for initial acceleration. So here is a charge q which is entering here to the right side with a speed of v, and the mass is also given small m, and it is entering into the region where you can find electric field is going from top to bottom like these arrows, and from the crosses I'm showing magnetic field. So it is uniform, it is given, it is not changing as it passes through, it is constant, both of them, electric field also and magnetic field also. What we need to find is, remember, initial acceleration. Now, how we can find acceleration? So we know from our Newton's second law that acceleration is F net force, divided by whatever the mass is. So this is for the second law, we can get the acceleration. But the point is we don't know the F net. What is the net force on this when it enters? Just enters the initial acceleration. What it will be that? So if we know the net force which is acting on this charge, you will be able to get the answers. So let's see which forces it will acted upon when it enters in this region. So first thing is there is a magnetic field, so there will be some magnetic force. And it is electric field also, so the electric forces will also apply. So what will be the magnitude? Let's discuss about the magnitude of both of them. We know that magnetic force is given by expression QVB sine theta. Here sine theta is not necessary to put because the the velocity is this side and magnetic field is going into the page. So they are at 90 degree. So sine 90 is 1. So we can keep this magnitude like just like that, QVB. What about the force? Electric force. So that is again, very simple expression, Q into E. So these are the two forces which will be there for this charge. What will be the direction? Because there are forces, we have to take care of the direction. That is important. Forces are a vector quantity. So now let's see if this happens, what will happen to the charge. So when it enters, I will draw here. Let's say it enters here, initial acceleration. So this is our Q charge. So what will be the direction of magnetic field? For that, you have to put your index finger in this side because the speed of charge is this side. Your middle finger to the bottom of the page. And if you see your thumb, that will be the direction of the force. So this will be the direction of force. This will be my force due to magnetic field. And the electric field is downwards. So the positive charge will follow only the electric field. So it will be pushed this side. So the forces for magnetic field will be this. We don't know the exact values. So we are I'm just generally keeping this vector, let's say like that. So that is my force of electric, right? But they are in the one line. So we can add them up with the signs. So I can say FB minus FE will be the net force. So this will be my net force. Okay, downwards as negative I'm taking, and upwards as positives. That's why the FB is positive and FE I have taken as a negative and I've added them up. So now our problem is almost solved. Now we can just go back to this acceleration, calculating acceleration. So we can say the acceleration will be FB minus FE divided by m. And now let me put the values. So it is QVB m minus QE divided by m. I can take, if you want to make it beautiful, I can take Q common. So Q is common now. So it'll be VB minus QE divided by m. So this is the acceleration expression we were trying to find. So please note it down. This is our answer. Let's see this question. In this, it has been asked that there is an electron moving. So this is an electron which is moving like from horizontal, it is 30 degree. It is given like it is going like that. The speed is also given 1.4 into 10 to the power 6 meter per second, and the magnetic field is zero point 0.7 Tesla. We've asked like what is the magnetic force? So that is what we need to calculate. So we know the formula for that. The magnetic field force is given by Q V B, and I don't have to use sine theta. The complete formula is sine theta, but sine theta I will not use because theta is 90. Even it is moving at horizontally at 30-degree, the angle between this electron, it is still in the horizontal plane, and the magnetic field is downwards, so the angle is still 90-degree. So this 30-degree is just to given has given us to confuse us. So will we factor it or not? So it does not matter. Even if it is 60-degree, still the electron will go on this plane, and the magnetic field is still downwards and making 90-degree. So it will not matter. Okay, so this is what the force will be, and that's what we asked. So now what we need to do is we need to put these values. So it will be 1.6 into 10 raised to power minus 19. Velocity I will plug in here, 10 raised to power 6, and the magnetic field is also given. So let me use my calculator for this. So the calculator 1.6 into 1.4 into zero point 0.7, 1.568. So 1.568 multiplied by 10 to the power, see it is 6 and it's minus 19, so minus 13 will be remain. This much Newton force will be experienced. So this is our answer. By the way, this 1.6 into 10 to the power 19 is a charge. This is the charge on an electron. So it is must be given in your formula sheet. If you don't, it's a very popular number, so you can remember it. 1.6 into 10 to the power minus 19. Let's do this question. This question is related to the Lenz's law. So what it is saying is there is a circular loop here. So this is a circular loop, and there is a magnetic field which is acting here into the page. So remember that the direction of that. And now we are pulling this out, so it will come out of this magnetic field. This dotted line shows the boundary. After that, the magnetic field, there is no magnetic field here. So we are pulling this into this region. What will happen? What kind of EMF it will generate? What will be the direction of it? And they have also asked like explain your answer. So think about it. When we are pulling this out, so the Lenz's law says the EMF will be produced in the direction such that it opposes the change. So always think about opposing opposes the change. So first, to oppose the change, we should know what is the change. When we are pulling this out, what is the change? So that is the explanation they are asking. So if we are pulling this out, I can say the B into the page is decreasing because a loop will come out, right? So the area of the loop which is under this magnetic field will go on decreasing, so will get lesser and lesser, and when it will come out it will become completely zero, right? So the magnetic field through this loop will decrease, right? And the direction is into the page, right? So we need to oppose this. Remember that knowing this what is happening does not make our answer right. So knowing this, we should know how, think about it, how I can oppose it. Now, how can we oppose it? So if into the page the magnetic field is decreasing, we should try to increase it. We should have some magnetic field into the page. So how to have that, right? So how to have that? So if you take this loop and uh, just take this straight part, grab it with your right hand going thumbs up, you will see the dot will appear here. Your fingers will be coming out from here. But if you keep your thumb down and grab this, you will find your fingertips will be striking here, creating crosses, or you'll be creating magnetic field into the page. Yes, that's what we want. That's how we will oppose. So the direction of current will be this. So you can think of just grabbing it. The current is going in this direction. And what is that direction? That direction is like a clockwise direction. So the answer for this problem will be clockwise. And why? Because when we are running clockwise current through this, the magnetic field will try to increase. Because when we are pulling out, it is trying to get decreased, and we are canceling that effect. We are opposing that change. So that is why the current direction, induced current direction, induced current current direction will be clockwise. Thank you. Now let's see this question. This question is very interesting. What it is saying that there is a magnet like lying like that. North side is this of this magnet, and one this magnet which is have seeing south side here. So what will happen due to this orientation? There will be a magnetic field north to south. Now what is happening is we are dropping one rectangular wire loop like this. We are just dropping it from the top. It will go down like that. So now they have asked like, oh, observe induced EMF. What will be its direction? Will the direction only one? Let's see. So to observe this, let's imagine when it was entering, this loop was entering into this field. Remember, our magnetic field is in this direction, right, toward right. And the when it will be entering this magnetic field, the magnetic field passing through this loop will increase in the start, right? So according to Lenz's law, this change in magnetic field should be opposed. So what we need is it will induce a current. Okay, so it will induce a current. Let's see when it is entering. Okay, when it is entering, it will induce a current so that it can oppose it. So now how it can oppose? Think about one side of this. Let's see this loop. Okay, and if you grab it with the right hand, you will see your loop, your fingers will curl like that going into the page, right? And that is what the opposition is. So north, to oppose north, we will oppose it like that, right? So if I draw a diagram like that, my fingers will be like curling like that. And don't ask me how they can be my fingers, but that's it, right? So this will be going into the plane so that I can oppose this change. I don't want this magnetic field running through me, increasing from north to south. So while entering, the current will be in this thumb's direction. So it'll be up. Okay, it'll be up. Let me rub this, and now we know. Right. So while entering, the direction of induced EMF will be up. Now what will happen? It'll go on increasing, but when the halfway of this loop has reached, what will happen? The magnetic field will start reducing, right? It while entering, it is fine, right? But while exiting, when it is trying to exit or coming out of this magnetic field, now this loop will see another change. Now the magnetic field will decrease, right? While entering, it was increasing, so we opposed it, right? So this is the change, we opposed it by decreasing it, by opposing the north pole. And while exiting, we will see a decrease in magnetic field. And when we see the a decrease in magnetic field, this loop will try to induce a current so that it can oppose that. What do you mean by that? So that it will try to generate magnetic field in the same direction. North to south is decreasing, it is saying. So it will create current such that the magnetic field is produced in the same side, north to south. And that can be when your thumb will be like that. This is the thumb, okay, and your fingers are going like that. So that is my rough diagram. Sorry for my drawing skills, but what I mean to say, the current will be in this direction. So this is while entering, and this is while exiting when it is moving out. So the current will switch its direction. So if we have some device where you can see the current, so it'll go up and down. Okay, so the current will go in one direction and then in the reverse direction. So this will be the direction of that. So we can observe they have asked like find induced EMF direction. Initially it will be in this direction. So we call that clockwise and then it will go anti-clockwise. So that is the observation for the induced EMF. See this question now. In this question, what has been asked is that there is an electron which is moving towards the right side and is entering a field region where magnetic field is there. So this is a magnetic field and the direction is shown by crosses. What does mean is that the magnetic field is into the page. Now they are asking what will be the direction of magnetic force. So in electrons, what I do is I solve it for positive charge. I don't get confused. So let's say if it is a positive charge, what will be the direction? Because that's what all the formulas are driven for positive charge. And let's find out this first. So if you see the direction of V is this, you will put index finger there, magnetic field will be downwards, put the middle finger on that side, and you'll see your thumb going up. So that will be the uh, direction of force, for on a positive charge. For electron, just flip it. Yeah. So that is why whenever there are questions which are involving electron, I solve it for the positive charge and then I flip the direction. So it was for positive charge, if it is upwards, then for the electron, it will be downwards. So that way we can solve this problem. So the electron will feel a force downwards. Thank you. Let us understand this question. In this, they are telling that there is a charge particle. There is a charge particle. They have not given us as positive or negative. They have just told that is a charge particle, say Q, and it is moving in this circle, right? It's a part of circle they have given to us. It is moving like that, and the radius is R1. So the radius is R1. Now what they're saying, what if we double the speed? So if it is going like this, now we increase the speed and we double it, what will be the radius? What will happen to the new radius? Will it change or not? So straightaway solution for this is whenever a charge particle is under a magnetic field, so it creates a circle which is having a radius of r is equal to mv divided by qb. So we can calculate the radius from this formula. So this is the mass of that charge. This is the velocity of that charge. This is the charge on that charge. This is the magnetic field. So we can see that we are not changing anything other than velocity. With the charge is same, the magnetic field is uniform given in the question, right? So this B is uniform. I should have told you before. So it is uniform. It is not changing. So it is moving in a uniform magnetic field. So this is also not changing. So everything else is the same. So I can say the radius will be proportional to, because everything else is constant, to the velocity. So if we I am doubling it, if I'm increasing the velocity to the 2 times, the radius will also get doubled. So we can say for this that radius will also be doubled. Now, some of you will be thinking like from where this has come. So I'll just give a small review here so that you remember that. So the charge particle when it enters a magnetic field, okay, so it moves in a circle with this radius. Let's say this radius r. Okay, and who is providing this centripetal force? Why it is moving in a circle? The magnetic force. So the magnetic force on this charge will be QVB. That is the magnetic force, right? And assuming that magnetic field is something like that, 90-degree, so that we don't have to care about the sign of, sine theta with this formula. So that is the QVB. Now this must be equal to the centripetal force. So that is the central idea how we are deriving this formula. So centripetal force, and we have a generic formula for that, and that is mv square divided by r. So let us equate it. QVB will be equal to mv square divided by r. V will be cancelled out, baby. 1b will cancel out here. And now let's solve for r. So I will take r that side, and then mb will be this side, qb will go down, qb, right? So this is how we can derive this formula. It has come because it is moving in a circle in the magnetic field. The centripetal force is provided by the magnetic force. So we equate it with the generic formula for centripetal force and we get this radius. And seeing that we are able to solve this, if you increase the velocity, double the velocity, the radius will also be doubled. Another interesting question. Here there is a wire going like this, and there's a loop given us. The area is given as A, and on the perimeter or circumference, the magnetic field is generally, in a general terms, given as B. Now, what they are asking is if we increase the area of the loop by 2A, so we double the area, what will be the magnetic field in this case? So let me say B, this one as B dash. Okay. So what will be the magnetic field here? Now remember the magnetic field around the conductor, we don't have any formula by area. We have a formula by the distance. So if this is the radius, let's say r, and let's say this is the radius r dash because doubled it, and somehow if we are able to figure it out that what is the relation between them, then we'll be able to find the magnetic field here as compared to here. So let's go through it. Okay, so the area of this will be pi r square, and area of this loop, okay, that will be double of this area, right? So b dash will be equal to pi r1 squared, right? This one, and this will be, this area will be double of this. So this will be equal to, we can say pi r1 square should be equal to double of pi r square. So now we can cancel out pi here, and we can say that r1 square will be equal to 2r square. And now I'm solving for r1. So r1 is square root of 2, and square root will cancel this square. It will come as simply r. So we have reached this conclusion that at this distance in terms of r is this under root 2 r. Now if somebody asks from the distance from this conductor, if the distance is under 2r, what will be the magnetic field here? We can use the generic formula for that. We know if there is a conductor, so around there will be magnetic field. If distance is r, the formula is mu naught I divided by 2 pi r. That will be the magnetic field. So now for this, it will be mu naught I divided by 2 pi 2 pi, and instead of r I can put under root 2r. So I'm simplifying it now. Under root 2 I will take out outside, under root 2 multiplied by mu naught I divided by 2 pi r. And guess what this is? This will be the magnetic field here, right? For the simple r, it will be the magnetic field mu naught I divided by 2 pi r. So I can put this value now, generic value b here instead of this. So it will be b under root 2. So that is our b dash. So that way we can solve this question. So what we learned in this question is like they have given the area, not the radius, but because our formula had radius, requirement of radius, so we calculated this r1 in terms of r so that we can apply this formula, generic formula, and then we got this equation. Thank you. See this question. In this question, the magnetic field is shown by the dots, so it is coming out of the page, and we have a circular loop. The area of this loop is given as 0.4 meter square, and at time t is equal to 0 when we start observing, the magnetic field was 3 Tesla. Now it is given to us that it is decreasing, the magnetic field is decreasing at the rate of 0.5 Tesla per second. So there is a reduction of magnetic field. Now, magnitude of the induced EMF in the wire at time t is equal to 0 when you are observing will be what? So that is what it is asked. So this answer goes to Faraday's law. And remember, the Faraday law tells us the EMF produced will be minus d phi by dt, right? So we are concerned if we know how much flux is changing and how much time it is taking for that. If we know that rate, we'll be able to find the EMF. Now, because the magnitude is asked, so we can ignore this sign because this sign only tells about the direction of induced EMF. So I will just erase it. So does not matter. Now, what about flux? We don't know the flux. We know B and A. So flux is nothing but a dot product of that magnetic field and the area vector. So it can be written as B dot product A, yeah, and divided by dt. Now the magnetic field is upwards, and we can take the area vector also by our convenience upwards. So the dot product will be cos 0, which is 1. So we can write it simply as further like d b simple multiplication by a. So that also is taken care. Now in this case, we can say the area is constant. We are not changing this loop's area, right? So we can take this a out of this change. So we can say area multiplied by dB divided by dt if is known to us. We can multiply it with that area and we should get the EMF, right? So can we have that? That is given to us. The magnetic field is decreasing at the rate of 0.5 Tesla per second. See the unit also, magnetic field divided by time. So this is given to us. Area is also given, so we will just simply put values now. So 0.4 is the area. It is given in meter square, so no need to change into the SI units. And then just multiplied by zero point 0.4. So it will be 0.2 EMF it is, so it will be volts. So that is what the answer, the induced EMF will be generated here due to the um, change in the magnetic field at this rate. Let's read this question. In this question, three wires are given, 1, 2, and 3. And also distance between them is also given. See, the distance is d between these two wires. Again, the distance, same distance is between them. And below this wire, the bottommost, again the distance d, if you'll go, you will find this point P. What has been asked is, what is the magnetic field due to three wires, all three wires at point P? So that is one is being asked. Now, how we will go about it? We will go wire by wire, see the magnetic field, how much they are exerting at this point, and also we will take care about the direction because that will help us to find the net magnetic field due to these wires. So first, let's talk about this. This wire has a current in this direction. Okay, this direction. So if we grab this wire with our right hand, thumb will be in the direction of the wire current, which is towards the right. You will find at point P, your fingertips will be going downwards. So the direction of magnetic field due to this will be, let's say this is case 1, this is case 2, case 3. So due to 1, the magnetic field will be cross here, right? Cross, and that will be mu naught I. Now I'm calculating the magnitude. So the formula we have is what is the mu naught multiplied by I, current going through them is I, divided by 2 pi multiplied by the distance. So distance is d. So instead of r, I will put d here. So remember, we are having both things, in consideration, magnitude, the formula, and the direction also. Okay. What about the case 2? So this is case 1 of the first wire. What about the case 2? So this wire, just see that. So this has a current, remember, 2I, okay? And the distance to the points P is 2D. Can we find the direction also? So if you will grab it, your thumb will go in this direction. Now, see, the direction is important of current. So the thumb, your right hand thumb will go in this direction. So you will see that at point P, your tips will be coming out of the page. So it will be a dot instead of a cross. So now let us apply the same formula. It will be mu naught. What is the current? Current is 2 times I. Remember that? So it is 2 times I divided by 2 pi and a distance between the wire and the point. So the distance here is t plus t, that is 2d. So it will be 2d. Let me simplify it. I can cancel out this, right? 2 to 2, and I can get, instead of that, I can write simply, it'll be mu naught I divided by 2 pi d. So this is for the second wire. Now let's see the third wire, what it does. So it is on the right side. So your thumb will point to the right side. And if you grab it, if you grab this wire with your right hand thumb going in this direction, you will find your magnetic field at this point is going into the page. So that will be the cross again at this point. And what is the magnitude? We will apply formula mu naught into the current. Current is 3 times I this time, and divided by 2 pi multiplied by the distance. So distance is d plus d plus d, 3d, right? Three dimension. Yeah, so we can cancel this out. So again, it is coming as, I can simply write, instead of that, I can write mu naught uh, I divided by 2 pi d. So this is due to the third wire. So we are clear now. We are done with the question, and we can write what is the net field. So now think about it. In these three, one is the all the magnitudes are same. Mu naught I, 2 pi d, mu naught I divided by 2 pi d. So the magnitudes are same, but the directions are opposite. So what will happen at this point? For example, let's say at this point, due to this wire, the magnetic field is going downwards with the same magnitude. And one component which is coming through the second wire is going upwards, dot, out of the page, but same magnitude. So they can cancel out each other. They will cancel out each other, and only the net magnetic field will be this. And also, does that cross is important? It was important because we understand that then only we'll be able to cancel them, right? Then only we'll be able to cancel and see. But in the question, they have asked only about the magnetic field magnitude. So remember that. What is the magnitude? It's been asked. So if they ask direction also, we can tell that direction. Okay, so that'll be into the page at point P. But if they're not asked, like in this question, they only ask about the magnitude, sorry, magnitude. So that'll be only this. So the net magnetic field will be mu naught I divided by 2 pi d. So that will be our answer. Thank you. So let's have this question as our last question for this video. So here there is a rectangular section shown in which the magnetic field is present, and I have shown with the dots. Remember, this is a uniform magnetic field. So dot is shown, it means it is coming out of the page. And these are loops. They are all identical. Okay, so their dimensions are 5 centimeter into 10 centimeter for all the loops, and they have a same speed. Okay, which direction they are going? All are going towards the right. So this is also going to the right, this is also going to the right with the same speed. This is also going to the right side. What we have asked is rank, we need to rank the induced EMF. Induced EMF. So at this instant, we need to rank. Okay, remember, like we can think of like what will happen in the next moment, just next instant, what will happen. So these all loops are at different, orientations, if you can see, and they are different positions. But what we can say about them? So we for induced EMF, we need some flux change. And for flux change, we should say like there should be some change in magnetic field. And that can happen if we change the area, right? So because this D, if you focus on, it is moving towards the right, but the area is remaining same. We have a uniform magnetic field. So for that, EMF at D will be equal to 0. Agree? If it moves here, even the same magnetic field will be there and same area will be there. So there will be no change in flux. So the EMF will be induced 0. What about this guy? C. C loop is also moving towards right. Remember, noting down the direction, right is important here. So if I'll just slide it like that with the magnetic field will change, which is passing through this. No, this will be only through this area, right? And it'll keep on same area. And it is uniform magnetic field. We are bothered about only at this instant, just next to it. We are not bothered like when it'll go out. Remember that. So if it is moving towards the right, there will be no change in magnetic field or even the area. So it is same. EMF due to C will also be 0. Okay. Now, what about the rest of them? See, this A, this B, and this E. Due to their orientation, you can see they are similar loops, they have similar dimensions. The change in area for the next movement will be same. Why? See, if it is entering, let's say in an instant, it takes this much thickness of area is changed. At the same time, because orientation is same and speed is same, this also elapse this much area. That will be the area change. So that much more magnetic field, the change will happen. Whether it is going out or it is coming in does not matter. We are bothered about the magnitude of EMF, not whether it is going in which direction. Same thing will happen with this. It will also elapse this thickness, let's say, right? So the change in area for both these and this E is same. So the EMF generated will also be same in this case. So we can say EA will be equal to E at E will be equal to E at B. So this is what the ranking looks like. We have forgotten one, F. What will happen in the case of F? Okay, how much this will be changing. So the at 1 second, let's say it elapsed this much according to that, right? How much that area change will be for this? So same thickness, right? Same velocity. Velocity is not changing, but you see the change in area is more in this case, right? In the case of F. Why? It is oriented, it is placed like that. So if you move it towards the right, more area is getting changed. More area is getting changed, more magnetic field change will be seen through this loop. So this is the main thing, or we can say the top ranker is this guy. EF will be maximum, will be maximum. Yeah. And these guys are minimum. Yeah, and these guys are in betweeners, right? Medium in betweeners. And we are talking about, remember, only about the magnitude, because it was not asked, they were just ranked us asked to rank the magnitude. Thank you.